Welcome back. We're going to talk about buffers some more here, and specifically we are going to talk about what happens when we add something to a solution that has a buffer in it. So if we already have a buffer in the solution and we go ahead and add some acid or add some base to the solution, what happens to the pH? Because like we said before, buffers are not perfect. Buffers work really well. They hold the pH much closer to stable than it would without it, but they're not perfect. So here's our game plan for working out the pH of a buffered solution after adding something to it. So when we add a strong acid or a strong base to a buffer, it's going to be safe for us to assume that all of the strong acid or base is consumed in the reaction. So none of it gets left behind, and this is really the same assumption we make just in saying that the acid is strong. We're just saying that it all reacts. There's none left behind. So what we're going to do is we're going to start with some information about the buffer. So we should know these two values here. We should know how much of the acid we start with, and we should know how much of the conjugate base that we start with. Now, the step that's added in technically has there is a technical difference from one thing to another depending on what we add, but really in terms of the actual mechanical process of working through the problem, it doesn't actually make a difference. So it will make a difference in that different molecules will react, but it won't make a difference in terms of the math. Like the process is going to be the same regardless. So for example, if we add in a strong acid, that strong acid is going to react with the conjugate base, and it's going to form more of the weak acid. Conversely, if we add in a strong base, that strong base is going to react with the weak acid and form the conjugate base. And water as well, but we don't really care about the water. The water's just going to go and be more of the water. There's already tons and tons of water. So the key thing here is that in either case, both the concentration of the conjugate base and the weak acid are going to change in both cases. The difference is, in one case the acid goes up and the base goes down, and in the other one the base goes up and the acid goes down. They're just flipped, essentially. So if we know how much of the acid and base we start with, we're going to figure out what reaction takes place and use that to work out what the new concentrations for the conjugate base and the weak acid are. So we'll have new values for those two. Those are the values that we are then going to plug into the Henderson-Hasselbalch. So this first step here is really just stoichiometry. What did we start with? How much is reacting? So then, therefore, how much of this step do we have left? Take those numbers, plug it into the Henderson-Hasselbalch to find the pH. So let's look at an example here. So we have a buffer that is made from adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make 1 liter of solution. And the pH of the buffer is 4.74. So that is our starting state. Now we're asked to find the pH of the solution after we add 0.02 moles of sodium hydroxide. So we're putting in a little bit of something to change the buffer a little bit. We're putting in 0.02 moles of sodium hydroxide. So what we're going to do is, just like I said, we're going to work out what are our starting amounts and then what are our final amounts once the reaction has taken place. So we're told in the problem we start with 0.3 of both of these, and that we add in 0.02 of the hydroxide. Now we know because hydroxide is a base, it's going to react with the strongest acid in the solution, which is not water, it is acetic acid. So the base is going to react with acetic acid to form acetate and water. So we're going to consume this, so its concentration is going to drop 0.02, and we're going to produce the acetate, so its concentration is going to go up 0.02, which leaves us with 0.28, 0.32, and 0 of the OH minus, because again, we're assuming all of it reacts. None of it gets left behind. So then these numbers are what we're going to take and plug directly into the Henderson-Hasselbalch. And so the pKa of acetic acid is 4.74. Those are our new, and actually there's a typo there, that should be 2.8. Sorry about that. That should be 0.280, not 0.2. I think I actually remember noticing this last semester, and I think the math is correct. It's just I had a typo there. But feel free to check me to make sure that that is just a typo and that there's not a math error. So then if you take the log of 0.32 over 0.28, you get 0.06. So you just add that to 4.74 and you get the new pH of this solution is 4.8. Now if you're thinking, okay, big whoop, the pH still changed, the buffer didn't work. Well, what if there hadn't been a buffer at all? What if you just added 0.02 moles of sodium hydroxide to water? Well, you wouldn't end up with a pH of 4.8, I can tell you that. You would end up with a pH of 12.3. 7.5 pH units difference. So yeah, the buffer worked. The buffer worked very, very well. It would have had a very different solution without that buffer in it. Okay. Let me see. Do I want to talk about that now? Yeah, I guess we'll go and talk about basic buffering system real quickly here. So the buffers that we've been looking at up to this point have been acid-based systems, where we had a weak acid and its conjugate base, and that was our foundation, so to speak, of our buffer. But you can do the same thing with a weak base and its conjugate acid. So it's actually fairly common to have, for example, ammonia buffers, where you have ammonia and ammonium, high concentrations of both of those, and that will produce a buffer that is for the base side of the pH range. And you can do this with any kind of weak base molecule. The one thing we do have to do differently, though, is that when we plug things into the Henderson-Hasselbalch, it still needs to be the pKa. The Henderson-Hasselbalch stays the same. There's no change to the Henderson-Hasselbalch. We're not going to switch to the pKb. We're not going to flip the base and the acid. Everything stays exactly the same. We just need to work out what the pKa of our base is, which I know seems kind of counterintuitive, but it's perfectly reasonable to do that. We just have to remember that the Ka times Kb is equal to Kw, and if we take the negative log of all that, it's just the pKa plus the pKb is equal to 14. And so it's not too bad, it's not too difficult to work out what the pKa of a base is using those equations. So let's do one example of that real quickly. So this says, use the Henderson-Hasselbalch equation to calculate the pH of a buffer solution that is 1/2 molar ammonia and 0.2 molar ammonium chloride. And it actually goes ahead and gives us the pKb, so we don't have to solve for that. Sometimes it'll just give you the Kb, and you'll have to find the pKb, but it goes ahead and gives it to us there. The first thing that I'm going to do is I'm going to convert this to pKa, because I know I'm going to need that for the Henderson-Hasselbalch. So given this equation here, that the pKa plus the pKb is equal to 14, I know that my pKa is 9 1/4. So the pKa is 9.25. I also know that the Henderson-Hasselbalch tells me that the pKa, or sorry, the pH is equal to the pKa plus the log of the base over the acid. And so, if I look here, it doesn't specifically say this is an acid, this is a base, but I know that ammonia is a base, and the ammonium is the acid. And if you're thinking, well, sure, you know that. You've been doing this for decades at this point. How do I know that? Well, it is a little more difficult with the bases, just because acids always have acid in the name, and bases do not have base in the name. But you can always tell what's the base and what's the acid by looking for what gained a proton, because the thing that gained the proton is the acid. So here we have NH3, here we have NH4. So this gained a proton, which means that it is going to be our conjugate acid. In the reverse reaction, it's going to give that proton up. So even if you're not familiar with the molecules themselves, you can always work out what's the base, what's the acid, because one of them will have one extra proton, and that's the thing that's going to be giving that proton up in the reverse reaction. Okay, so then, if the ammonia is our base, pH is going to be 9.25 plus the log of 0.5 over 0.2. And if I do that math, let's see. Log of 0.5 divided by 0.2. 9.25 plus that value. My pH is 9.65. So a slightly basic buffer. Not terribly basic, but that's fine. We didn't need to be terribly basic. Alright, we'll call it there for this video, and the next one we'll talk about the capacity and range of buffers, which is essentially the best conditions that buffers can work in. Because like we've been talking about this whole video, buffers are not perfect. They have limitations, and so we're going to talk about more of those in the next video.